Today we're going to talk about the thermodynamics of CO2 sequestration. Coal is a heterogeneous substance whose exact composition depends on the geographical location of the mine. The best coal is anthracite or hard coal, such as that from mines near Shamokin, PA, which is virtually all carbon and hydrogen with a small amount of oxygen. More conventional bituminous or black coal, such as from the strip mines and deep shaft mines in China, releases less heat when combusted and contains a tar-like substance known as bitumen, with more nitrogen and sulfur in it. Lignite or brown coal, such as that found in the Lausitz in Germany and the Latrobe Valley of Australia, has the lowest calorific value. It contains many impurities, especially sulfur, and a good deal of water. So now, what is the approximate molar mass and chemical formula of coal? Well, let's assume that we're working with a sample of anthracite that is 95% by weight carbon and 5% hydrogen. If so, then a 100 gram sample contains 95 grams of carbon and 5 grams of hydrogen, or dividing through by the molar mass, we'd see we have 8 moles of carbon and 5 moles of hydrogen when we round up to the next integer. Therefore, the molecular formula of our coal is essentially C8H5. Now, that this effectively is the lowest common denominator for the molecular formula of coal. Without structural data, it's impossible to determine whether the average coal molecule is C8H5 or some larger unit such as C16H10. The molar mass is then about 101.1 grams per mole. Now let's calculate the enthalpy of combustion of coal. The calorific value, that is, the amount of heat given off upon combustion, is 3.26 times 10 to the 4 kilojoules per kilogram. You always have to have a balanced chemical reaction to determine the reaction enthalpy in order to determine what per mole means. The combustion reaction is 1 molecule of our coal, C8H5, plus 37/4 of O2, gives you 8 moles of CO2 plus 5½ moles water. That is, 8 moles of CO2 are produced per mole of coal burned. The enthalpy of combustion is the amount of energy in the form of heat derived from burning 1 mole of coal. So we take the calorific value multiplied by the effective molar mass, and we'll find minus 3,282 kilojoules per mole. Note that this is a negative number because it's an exothermic reaction. The delta H change, the enthalpy change, is negative for an exothermic reaction. Next, let's calculate the volume in cubic meters of CO2 that's formed when we burn 1 metric ton of coal. To find the volume, we use the number of moles of coal per ton of coal and the reaction stoichiometry to find the number of moles of CO2 produced. Then we'll use the ideal gas law to get the volume. So start with a balanced chemical equation again, and then multiply the number of moles of coal produced by 8 to arrive at 7.9 times 10 to the 4th moles of CO2 per metric ton of coal burned. Now rearrange the ideal gas law to find the volume, which will be about 1.9 times 10 to the 3 cubic meters of CO2 per metric ton of coal burned. Next, let's look at the annual production of coal in the US. It's about 1.1 billion metric tons. How much energy and how much CO2 is produced when this much coal is burned? To calculate that, we first calculate the energy released in the form of heat on burning the coal. That will just be the amount of coal times the number of moles of coal per metric ton times delta H on a molar basis. That leads to 3.57 times 10 to the 16th kilojoules, or 35.7 ectojoules released in the form of heat. The mass of CO2, that will be the amount of coal burned times the in metric tons times the number of moles of CO2 per metric ton times the molar mass of CO2 to give us 3.8 times 10 to the 15, or 3.8 petagrams of CO2 are formed, which corresponds to 2.1 times 10 to the 12 cubic meters. Now let's look at that sequestration process and ask, what is the amount of energy required to sequester CO2 per ton of coal burned? Well, to sequester CO2, you have to inject it into the ground. You have to compress it and heat it to form supercritical CO2. Then you inject it underground. The CO2 will have a final pressure of 6,200 kilopascals and a final temperature of 45 degrees C, which corresponds to 318 Kelvin. To determine the total energy, or at least the minimum energy required to do this, we'll have to calculate the work done to compress the gas to 6,200 kilopascals and the amount of heat required to heat to 318 Kelvin. Even if the process is done all at once, for the thermodynamics, we can break it up into two steps. First, a reversible isothermal compression, followed by isobaric heating, that is, heating at constant pressure. For a reversible isothermal expansion, we know the formula for work, and therefore we could calculate the initial and final volumes. However, let's note something from the ideal gas law. The volume is related to the pressure, and therefore we can calculate what the volume is from the pressure, but we don't actually need the volume, because we can substitute into that from the ideal gas law into the work equation, and what we'll find is that the work required is actually related to the ratio, the log of the ratio of the final pressure, the initial pressure to the final pressure. Running through the numbers, about 8 times 10 to the 8 joules per metric ton of coal is required to compress the CO2 to its final pressure. The energy required in the form of heat to raise the temperature of the gas, well, that will be equal to, the heat is equal to the number of moles times the heat capacity times delta T, the change in temperature, which will be about 5.9 times 10 to the 7 joules per metric ton. Finally, we'll sum this all up. The minimum energy required to sequester CO2 will be equal to the work plus the heat. That is, it's the same thing as the internal energy change of the CO2. So to sequester CO2, it would then, this amount of CO2, a metric ton of CO2, it will take a roughly 8.7 times 10 to the 8 joules per metric ton, and that is dominated by the work required to compress the gas. That term is about an order of magnitude larger than the heat required to raise the temperature.